Hello. Uh,
You are currently the only person in this conference.
Hello, Vivek. Is this your first class? Am I audible to you? Okay. Shreya, are you there? Okay, fine. I was just waiting for someone to just join. Okay, then let's start with today's session. Any questions from last session? Right. Let's start with today's class then. December 10th, right? Today I'll start off with the propositional logic. We give a simple definition of this. It's a branch of mathematical logic that studies the relationships between propositions. Okay. So another word for this proposition is a statement. It can be an assertion also. So this proposition, it is taken as a whole and it's connected via logical connectives. Okay. So some other names for this is that is proposition logic. It's called as sentential logic. Propositional calculus also. And combination of these two, sentential calculus. Okay. So let's look at some definitions here. The first one is this proposition itself. As I mentioned, it's a statement taken in its entirety. Okay. This is in contrast to the syllogistic logic, that's Aristotelian logic that we saw in the last class. Let's call it syllogistic logic. Okay. So I said this, the individual terms, they matter. And this statement, it's either true or false. Okay. I can take an example. All elephants are green. Obviously, this is a false statement, and that is all that matters if you are looking at it from a propositional logic point of view. Okay. In propositional logic, this animal, elephants, color green, they don't really have any importance. Next comes the propositional letters. Okay. So we simply use capitals for this. That is this above one. If I write, I can write this as A. Okay. All elephants are green. Next comes the truth value. So it's either true or false. We can use and say 1 or 0. Okay. Binary also is possible. Okay. Then V of P. Okay, this one will evaluate a proposition P. Okay, so it will return the truth value. Next come the connectives. These, they represent the relationships between the proposition. You guys, are you aware what all connectives are there? How many connectives are there? Or at least name a few. Yes. Negation, then conjugation, disjunction, and conditional and biconditional. Okay. With a symbol. Negation, it's either this or I can use a tilde. Conjugation, disjunction, they are opposites. Disjunction is a V, conjunction is an inverted V. Conditional has an arrow, biconditional has 2 arrows. Coming to the description of each of these, negation is essentially a NOT gate in digital electronics. You see, AND gate, OR gate, Conditional we don't directly see. This is an if then. And biconditional is if. That is if and only if. One other thing I'd like to mention now. You guys have heard of necessary and sufficient condition? Necessary and sufficient condition. Have you guys heard of? What does this mean? If the condition is necessary, then if you were to explain it in your own words, if I say a condition is necessary, what does that mean? Is my question clear or not? Okay, fine. I simply make this statement and move ahead. This if and only if, it actually encompasses this entire concept of necessary and sufficient. Okay. So this only if part, this corresponds to the necessary part, and if it corresponds to the sufficient part. Okay. So if a condition is met, meaning that condition is sufficient for the consequence to follow. And if I say only if, then that condition becomes necessary. Is it clear what I'm trying to say? Necessary and sufficient condition for consequence to follow the condition. Right. So for conditional, let me give an example. So it rains, Jeep won't walk to school. Okay, so I split this into two propositions. It rains. The second one, Jeep won't walk to school. Okay, so this entire thing I can write as A implies if then. Right. Moving ahead, let's look at the fifth concept, or truth table. So this one, it helps visualize the truth values. So for example, I can take let's say A as Marty wears green boots, D as Marty has a dog, and C as the conjunction of this. Marty wears green boots, and Marty has a dog. Okay, so if I make the truth table for this, B and C, so let's say A is false, B is false, A is false, B is true, true and false, and true and true. It's two statements and two truth values for each of them, total 4 combinations. So what will be filled in C? What should I fill in C? Quickly answer so that we can move ahead. F, and T. Since this is an AND gate, just 0, 0, 0, 0 and 1. Okay. I'm taking really simple examples. However, the initial part I've done by myself. Thing is, when it comes to this propositional logic in gate, specifically for this DA paper, even to some extent CS paper, making sense of these statements, that is also part of what's expected of you. Given an expression, evaluating this thing, it's very easy, but getting to such an expression, that will also be your task. Another way of writing this is, instead of false I can write 0, and instead of true I can write 1. So 0, 0, 0, 1, 1, 0, 1, 1, and it is 0, 0, 0 and 1. Okay, so one of these two you can use. Let's look at the types of connectives. First one I'll take is negation. So yeah, I think I can ask one question. We've listed all the connectives over here, right? How is negation different from all the remaining 4? Negation is on one side. These 4 I can put on another side based on one property. How is negation different from these 4? Injunction, disjunction, conditional, and biconditional. And give even one more clue. I think you should be able to get the answer after this. These 4 are binary operators, right? You need 2 of them. Yeah. But negation, only one is enough. So what should I write here? It's not binary, then it is it's a unary logical connective. Okay. So let's say P is the proposition. Then its negation is denoted as negation of P. Okay. And regarding the value, can I say value of negation P I want, right? So this is again 1 or 0. It is 1, the value of P is 0, and it is 0 if value of P is 1, that is otherwise. Okay, is what I've written here clear? It's a very simple concept only, but with proper notation. Fine. Truth table, the negation of P is 0, then 1, 1, then 0. We'll take one example. I take P as the moon is made of green cheese. The negation of P will be the moon is not made of green cheese. The examples that I'm taking right now, they are simple enough that with intuition you can easily tell. But as we move ahead with for more complex sentences, interpreting it will become at least a little bit harder. Okay, then move to the next one. Conjunction. Okay, so this one is a binary logical connective. I'll ask one more question now. Forget by conditional for the moment. Among these three, these two have a property that conditional doesn't. What is that? If I take two propositions A and B, I find conjugation, this conjunction, disjunction, and conditional. Conjugation and disjunction, I can find one pattern that doesn't exist the conditional. What is that? Vivek? Neha? You guys know?
Yes, sir.
I'm discussing connectives, right? I mentioned that this conjunction, disjunction, conditional, biconditional, they are all binary. However, if I take just these three, conjunction, disjunction, and conditional, there's a property common between the first two, but the conditional, it is a little different. What is that?
सर मेरा पहला लेक्चर है आज एआई का न्यू एडमिशन
Sorry?
मैं न्यू एडमिशन हूँ मेरा एआई का पहला लेक्चर है
Okay. Have you seen all this before? At least. I mean, it's not. Huh?
हाँ थोड़ा बहुत याद है सेम 6 में पढ़ा हुआ एआई सब्जेक्ट था
Okay. Okay, fine. Others? Fine. I'm asking actually really simple questions. It's a binary logical connective conjunction. It's also associative. Logical connective. What do I mean by associative? Sapna? These are the beginning classes. You guys should at least interact now. The easy questions you should be able to answer. What do I mean by associative? Someone answer this. Are you guys there or not? This thing at least I want to know. Swapna, Sneha, I'm audible to you, to the two of you. Yeah. Do you know the answer to the question that I'm asking? Yeah. This is associative for three propositions. We can take it for two also. Essentially, that becomes commutative property. Whole point is that the order doesn't matter. If I take two propositions P and Q and Q and P, they're both the same. I'll write that. Fine. So the property is this is true if both the propositions are true. And the value, let's say, of A and B. If I'm going to define this, it's going to be either 1 or 0. That is 1 if the value of B, this is 1, and value of A, this is also 1. And otherwise, it is 0. Let me take the truth table now. Zero, 0, 0, 1, 0, 1, 1, and has this. Okay. What did I mention? And B and A, these are both C. On to the next one, disjunction. And the symbol I've already mentioned, it's fine. So this guy, that is also associative. So this is true if either of the propositions is true. Just one is enough. Okay. And let me write it in an equation form. So it is 0 if value of B is 0 and value of A, that is also 0. Otherwise, it is 1. Okay. So the truth table, what will it be? 0, 1, 1 and 1. Correct? Any doubts here? One other thing, it's associative also I mentioned. So A and B or B and A, these are both the same. One other thing I should mention, this definition that I gave, this is an inclusive definition. Okay. What do I mean by this? The right question is, what if it was exclusive? Okay. The definition was exclusive, what would happen? If I said that the definition was exclusive, what change would I have to make in the truth table? No one? You guys know or not? Right? If I say that the definition that I given true, if either proposition is true, if the definition was exclusive, we'll essentially get an XOR gate. What do I mean by this? XOR gate truth table, what will it have in the last row? Yeah, last row it will have 0, meaning exclusively the inputs they have to be 1. Okay, if both are 1, then it will again become 0. Okay. We have the habit of calling it XOR gate. The naming behind it, it's coming from exclusive, and that exclusive is coming from this definition. Okay. So in disjunction, if it is mentioned XOR from digital electronics, we can quickly jump to that. But if I say exclusive disjunction, just to confuse you with some terminology, you should be able to know that it is XOR. Fine. Okay. We give an example here. The elephants are green. Or George wears green boots. Okay. This statement, it will make sense. We take this as E, this one as G. So what am I getting? E or G. If I was dealing with digital electronics, this wouldn't make any difference. But since we're dealing with natural language, what if both are happening? The elephants are green, that is also true. And George is wearing green boots. Okay, and this thing we don't know. So that exclusive part, what about that? Are we clear on that? Exclusive meaning the last one. Thing is, we are not clear. So I'll have to mention it is or both. Okay. If I just give this disjoint sentence, then it is not clear what should happen when both are true. So while writing the sentence, I'll have to mention this or both. Clear why I have to mention this or both? It's to clear up the inclusive or exclusive definition. If I don't mention this, then there's room for ambiguity. Come to the next one, conditional. This is equivalent to the if-then statement. Okay. So the result is true if the statement is consistent with this above format. Okay. Fine. Then this is only inconsistent in one situation. And what is that? Let me start writing the truth table also. 0, 0, 0, 1, 1, 0, and 1, 1. So what should I fill here? The last column. One, 1, 0, 1. So now I think you can answer. When is it inconsistent? What are the values for A and B for when it is inconsistent? Yeah, A is equal to 1, B is equal to 0. Let's say false and true. These are really simple questions. Thing is, this is another way of viewing conditionally. Okay. So what does this mean? So A is implying B. So A, I can call it as the premise, B as the conclusion. Okay. From here I can make a few statements. If premise is only false, then this conditional following it, the conclusion following the premise, it doesn't really make sense. So the conditional, this connective, it is always true. Is the statement clear? The premise is false, so whatever assumptions that I'm making, then this conclusion, it doesn't have any dependence on that premise. So the conditional, it'll be true. Okay. However, if the premise is true, then we have to be a little careful. If the premise is true and the conclusion is true, then the condition will be true. And the only issue will happen when something true is implying something false. Right? Let me write the equation. Value of P implies Q. Again, only 2. So when is it 0? When value of P is 1 and value of Q is 0. And it is 1 otherwise. So this P implies Q, another thing I need to mention, I can write this in using these 3 other connectives: negation, conjunction, and disjunction. How can I do that? Yeah. This is equivalent to negation of P of Q. Let's quickly verify this. PQ, then negation of P. I'll take the last one also. Negation of P or Q. 0, 0, 0, 1, 1, 0 and 1, 1. Negation of P is 1, 1, 0, 0. The negation of P or Q. So this is 1, 1. Over here both are 0, only then it is 0. Finally this is also 1. Fine. Any doubts in this? It's a really simple one, but this was a previous year GATE question also. Seriously, this concept was asked last year only. Mention this. In DA 2025, one question was there. I think I can mention it over here. Yeah. Let P and Q be two propositions. So consider these statements. S1, it says P implies Q. S2 says negation of P and Q. S3 saying negation of P or Q. And S4, negation of P or negation of Q. Okay. So which one is correct? It's an MCQ. Option A, that S1 is equivalent to S3. B is S2 is equivalent to S3. S2 is equivalent to S4 and D is S1 is equivalent to S4. So which one is correct? Yeah, E is the correct answer. And moving ahead. Let's do one more example on this. So 4 cards are on the table. So each has a number on one side and a colored patch on the other. Let me say that the visible faces, they are 3, 8, the color red and the color brown. And I have the proposition. If a card shows an even number on one face, then its opposite face is red. Now to test this, which card should be turned over? Now I think you'll have to actually try a little hard to solve this. I've given a proposition, I've given the full scenario, I've given this fact also, that each card has a number on one side and a colored patch on the other. You're able to see 3, 8, red and brown. So which cards should be turned over? We can call this card 1, card 2, card 3 and card 4. Can you answer this? Should I start with the solution? Guys, are you there? Are you trying this? Okay, fine, try. Take some time. Let me start with the solution. Answer. If a card shows an even number, card shows even, then opposite face is red. Okay. So this first one I'll take as P. Second statement I'll take as Q. So the whole statement will become, our proposition is P implies Q. If the card shows even, then the opposite face is red. Okay, so only one card you need to turn over, Shreya. Only one card you're saying then. Okay. And let me analyze. Let's see where we get. We have P, Q, and P implies Q. One, 0, and 1. So one card as well. So two cards. Yeah. So let's analyze case by case. Card 1, this is 3. 3 is an odd number. Okay. So since it is odd, card showing given this P, it is false only. So this becomes not relevant because the premise is false. Okay. So I have P equal to 0. This will give me P implies Q as 1. Next, card 2. Eight, which is even. So this is relevant. So since it is relevant, I'll be flipping this. Okay. So this will correspond to the case of P equal to 1 and P implies Q. We don't really know the value. It can be 0 or 1. And the third card, this fellow is red. Okay. So this card 3, is it relevant or not? Not relevant, correct. And why is that? I'm having Q equal to 1. So at Q equal to 1, these two entries are relevant, right? These two. The output is already 1. So P implies Q is 1. So what does that mean? You flip the card, don't flip the card. This proposition, it has already yielded a true value. Okay. Final one, the brown card. What's happening here? Q is 0. So for Q is 0 case, P implies Q, it can be 1 or 0. Okay. And this is what is making it relevant or not. Right. So because of this card is again relevant. This is making it relevant, and a fixed value of P implies Q, that is making it not relevant. Is the line of reasoning clear to everyone? So the final answer is both these cards, card 2 and card 4. These two need to be flipped. To the next connective, biconditional. This I said it is if is equal to if and only if. The shorthand notation of this phrase is IFF. What does this do? It checks if both propositions evaluate to the same truth value. Truth table P and Q now. I'm interchangeably using A, B, P and Q. Hope that's not causing any confusion. Just from the random letters. 0, 0, 0, 1, 1, 0, and 1, 1. So what should I fill in the last column? What goes in the last column? Propositions from both sides, they should be true. Two arrows are there. P implies Q and Q implies P. Okay, so 1, then 1, 0, 0, 1. The previous case, it was true implying false, that was the issue. Here the false and true value, that's also a problem because Q implies P, that is also evaluated. Fine. So I can write one statement here. This P by implication Q, this is equivalent to P implies Q and Q implies P. Okay. So is it clear? My initial statement, what I said, checks if both propositions evaluate to the same truth value. Means if P and Q are equal, they are both 0, then it is 1. If they are both 1, then also it is 1. In this form, I think I can write this is equal to 1 and 0. What should I write over here? If what condition should I write here? For this condition, I had written V of P is 1, V of Q is 0. Here, 0, 0, 1, 1. So here, what should I write regarding the values of the propositions? I'll be putting in the statement only over here. V of P is equal to V of Q. Otherwise, it is 0. In digital logic, what is this gate? Digital electronics, this is the truth table of which gate? XNOR, exclusive NOR. So let me take one example. I have one more point to make here. We will cancel the parade. If and only if it rains. Okay. So an equivalent way of saying this is, so if it rains, we will cancel the parade. And if we cancel the parade, then it is raining. Okay. This initial part, cancelling the parade, I can take as P. Raining, I can take as Q. What is this one saying? Q implies P. or P implies Q. An important point that I wanted to make here is this one, it doesn't imply causation. What do I mean by this? If this thing happens in real life, we know that because of the rain has caused the parade to be cancelled. But when we are dealing with propositional logic, there is no place for this causation here. Okay. So there is no causation. It just means that if it is raining, if it isn't raining, we will definitely hold the parade. Fine. Is it clear? The point that I'm trying to make about causation? There is no room for this causation in propositional logic. Fine. Let me take one more example. I can say in a triangle, let's say an angle is 90 degrees. In statement B, I'll say the sum of squares of two sides is equal to the square of the other side. Right? So if I take A implies B, what is this? If an angle of a triangle is 90 degrees, then sum of squares of two sides is equal to square of the hypotenuse. Pythagoras theorem, right? If I take B implies A, what will this be? This is from a point of view of logic. This will be converse of the theorem. Okay, and if I combine both of them, I'll be getting A being equivalent to B. Right. To the next topic, we'll briefly see what well-formed formulae are. So called as WFS. Okay. So this has to do with building complex propositions. These complex propositions, they may be constructed by combining simple ones. Right. For example, we can have negation of A and B or C. Okay. For doing such constructions, there are some rules. Rules for found formulae. This first rule, any atomic proposition is a well-formed formula. Okay, WF. Next one, let's say if A is well-formed, then negation of A, that is also well-formed. Then if A and B, they are well-formed, then their conjunction, that is also well-formed. Right? And this will repeat. Then the disjunction is also well-formed. Then the implication, that is also well-formed. And the by implication, that is also well-formed. So total 6 rules I've written here. One more rule is remaining. So unless constructed using above rules, a proposition isn't a well-formed formula. So let me take 3 examples for this. It's a very simple concept, but there needs to be certain rigor since you're dealing with logic. So out of these 3, which are well-formed or which are not well-formed? A really simple question. Now you can give this definition of well-formed also. Just look at these 3. Which one is problematic? Is it intuition? One of these 3, it has a problem. And what's the problem? Yeah. So this one is wrong. The reason is A negation P, this is not valid. This negation is a unary operator. Right? Moving ahead. Tautologies, contradictions, and contingents. Let's start with tautology. Anyone knows what a tautology is? Tautology always evaluates to true. It is always true for all truth assignments of the atomic propositions involved. For example, it is either raining or not raining. Okay. I think in the last class I had mentioned this kind of thing. What is this law called? If I take P as it is raining, then P or negation of P. What is this thing called? P or negation of P. Did I cover this in the last class or not? You guys remember or not? I think that's a more apt question. This is called the law of excluded middle. Right? This phrase, this law, you remember? Is the name at least? At least answer yes or no. Okay, fine. What was something else that I had mentioned? The double negation, right? So we'll take negation of negation Q. So this Q and the negation of negation Q, they're equivalent, right? So this entire expression, this is also a tautology. Is it clear how this is a tautology? Okay. Let's construct a truth table and do one example. Let's take this A and B. This implies C. The by implication. A implies B implies C. To check whether this is a tautology or not. To do that, simply construct the entire truth table. So 0, 0, 0, 0, 0, 1, 0 1 0 0 1 1 1 0 0 1 0 1 1 0 and 1 1 1. Next I'll take A or B, A and B. It will be 0 0 0 and 0 0 0 again here. Only in the last two cases it is 1. Next, this thing implying C. So false implies false, that is true. False implies true. Premise is false, we don't really have to worry. It's always 1. Correct? The premise, that is A and B, that is false. Then the outcome of the implication, the conditional, that is true. Over here only, we have to be a little careful. Over here, true is implying false, so it is 0. True is implying true, that is 1. Is it clear? Clear specifically regarding the first 6 entries. Now I quickly jump to being 1. Fine. Then let's go to B implying C. So wherever B is 0, I'll simply put 0 first. 0 and 0. B implies C. Over here, oh sorry, it's supposed to be 1. 1 1 1 1. True implies false, that is 0, and this is 1. Yeah, this is essentially a copy only. 1 1 0 1 1 1 0 1. Then I'll go for A implies B implies C. Last column, I'll take this entire thing as F and I'll evaluate. Fine, so A implies B implies C. A is 0 here, so I can blindly put all 4 values as 1. Then over here I need to check. 1 implies 1, true implies true. Second is also true implies true, this and this. Third is true implies false, this is 0. Last one is true implies true. So this is 1 again. And to evaluate F, what should I do? I need to check this and this. So I'm going for by implication, I won't go for the truth table. Using some shortcuts, I'll do it. What I'll do is just check if both are the same. This we have, right? If the values are equal, then it is 1. Otherwise, it is 0. So both are equal, 1 1. So it is 1 1 and 1, again 1 1 1, again 1. And over here, it has turned 0, but A implies B implies C, that has also turned 0. Values are still same, so it is 1. This is also 1. So this F, this is a tautology. Any doubts here? Go ahead. What's the contradiction? This one is always false for all combinations of input. Okay. For example, it is raining and not raining. Both of them, they cannot happen at the same time. So it's a contradiction. One way to make contradictions if you simply take a tautology and negate it. Okay, so this entire thing, if I negate negation of A or B implies C being equivalent to A implies B implies C. Okay, so this is a contradiction now. Next one, contingency. What is a contingency? A proposition is contingent, then what? Can you guys take a guess? One is always true, one is always false. What is the third category? If it is neither a contradiction or a tautology, both true and false, that can't really happen, right? Yeah, it can be true or false. If it is neither a contradiction or a tautology. Anyway, your answer, it has given us room for highlighting one thing, that any proposition, it is either true or false. It being both true and false, that kind of thing we saw in the last class, right? There was that paraconsistent logic, dealing with paradoxes. So those kind of things, they don't have any room for, we don't have any room for that in propositional logic. Right. So let's take one small example. I want you guys to evaluate this. A and B being equivalent to A or B. I call this as G. Since there are only two variables, 4 rows will be there. The final column, what will be the values? You guys quickly tell me that. Vivek, can you do this fast and tell me? EB, take and then or, then go for the by implication. Is G. What will this last column have? I want you to tell me, Vivek. Vivek, are you there? Okay. So I'm taking and here, 3 zeros, then 1.
0001 01 0111.
Okay. And what should I fill in this last column? This G will be by implication. So false implies false, that is true. Now they are not equivalent, they are not equal, so these are 0, this is 1. Any doubts in this? Anyone? Neha? Are you there, Sneha? Any doubts here?
No, sir.
Fine. Let's take another example. Negation of A and negation B. Okay. So tell me if this is a tautology or a contradiction, or whether this is contingent. So given an expression, it has to be one of these three, right? This is a valid expression also. It is well formed. Okay, final one is there. Right. Okay, evaluate this. How did you guys solve this? Priya and Sapna? With the truth table, simplification, truth table only. Okay. Any other method of solving this? Fine, I'll come to that in a minute. So A of this 0 0 1 0. Right. Negation of this 1 1 0 1. A plus B is also 1 1 0 1. And since these two are equal, this by implication will give me all as ones. Therefore, it's a tautology. Another thing I'll mention, logical equivalence. Okay. So A and B, they are equivalent if and only if this by implication is a tautology. I'm essentially saying a very simple thing in a complicated way over here. In natural language, if I say A and B are equivalent, what does that mean? If two propositions are equivalent, then what can I say about the truth values? They're always going to be equal to each other. And the definition of this biconditional, I mentioned this, right? This one. So if it's always one, that is, if the value is always equal between the two, then there's no scope for this other case. Essentially, we'll be getting a tautology only. Fine. So this is a biconditional. I have the habit of calling it by implication also. You can also call it equivalent. Right. So other way of solving this is by De Morgan's laws. I'll come to that a little later, but I think you guys will already know at least a little bit. So if I apply De Morgan's theorem to this, what will it become? Yeah, negation of A or B. And this negation of A or B, that is equivalent to A implies B, right? I just saw that over here, right? Over here I use this triple equal symbol because I had not introduced this biconditional yet. So the same thing we are taking and making it into a tautology over here. Fine. Okay. Moving ahead, let's look at some identities. And start with the law of excluded middle. Always good to write this simple laws a few times. P or negation of P. What about contradiction? P or negation of P. Fine. Third one, modus ponens. If I have P and Q, how will I write this? I don't know if you guys already know this. You guys know the expression for modus ponens? Modus ponens essentially says P implies Q, and I know that P is true. Okay, this means that Q is also true. So it's not like you don't just memorize this expression, you have a certain thinking behind it. Next comes modus tollens. You can think of this as a contrapositive kind of thing. P implies Q, and I know that Q is false. Okay, this means that P is also false, because true cannot imply false. Is it clear? These two? You guys have seen both of these before, right? Modus ponens and modus tollens. Moving ahead, there's double negation. This we have already seen. Negation of negation P is equivalent to P itself. Then law of syllogism. If we say, I know that P is implying Q and that Q is implying R. So if I combine these two, I get that P is going to imply R. Okay. Next one is decomposing a conjunction. Okay. This one is P and Q, right? This one implies P. Right? Meaning among P and Q, if at least if both of them are true, right? For and I need both of them to be true, it means that P is obviously true. So hence P. And the same statement I can say about Q also. Both of them are true, hence Q is also true. Okay. So this conjunction I am essentially splitting it up. I am decomposing it. Next one, constructing a disjunction. So it's essentially the other way around. P, if I know that P is true, I can take it conjunction with any other proposition. It is still going to be true. Same with Q. Q will imply P or Q. Are all these identities clear? Decomposing and constructing? Writing the expression is one thing, the logic behind it. Next, let's go for definition of biconditional. You've already seen this. E being equivalent to Q. This is the same as P implies Q or Q implies P. Fine. Next, commutative law. Or conjunction. Can you guys tell me what the expression I should write for P and Q? and that equal to symbol in the middle, replace it with a biconditional. These two are logically equivalent. Is it clear? Okay, so putting this biconditional, the by implication as logical equivalence, it's a fairly powerful tool if you understand it well. Same way for disjunction, P or Q is logically equivalent to Q or P. Next we go for associative law for conjunction. So what can I write here? Let's take three propositions P, Q and R. Then again that equal to sign we simply replace with the by implication. So P or Q or R, this is equivalent to P or Q or R. Or here P and Q and R is equivalent to P and Q and R. Next, let's go for De Morgan's laws. Negation of P or Q. This is equivalent to negation of P and negation of Q. Other one is negation of P and Q is equivalent to negation of P or negation of Q. Next comes distributivity. What should I write for this? Now follow formal notation for a moment. What is distributive law? Even we can take even digital electronics. How does the distributivity work over there? You guys know this or not? Distributive law. Come on guys, answer something. Yes, that's correct. P and Q or R, this is equivalent to P and Q or P and R. And the other way also it works around. P or Q and R, this implies P or Q and P or R. Next comes contrapositive law, law of the contrapositive. This essentially tells us that if P implies Q, then this is logically equivalent to negation of Q implying negation of P. Next one, conditional disjunction. Just a fancy name for something we have already seen. P and Q and negation P or Q. Both of these, they are equivalent. Next one, disjunctive syllogism. What does this say? P or Q, and I know that P is false. Okay. Now between P and Q, one of these it has to be true, and I'm knowing that P is false. So what conclusion can I draw from this? Don't look at the formula also, listen to my words. I have two propositions. One of them is true, at least one of them is true, and I know that the first one is false. So what can I say about the second proposition? Yeah, the second proposition is true. So this one, it implies Q. Is the logic clear behind this expression to everyone? It should not be like you're just blindly memorizing it. You should be able to make sense of what you're writing. Next comes a simplification. One says that if I take OR with itself, it's equivalent to P only. Same with AND, the conjunction. This is also equivalent to P. Next one, let's go for this law called resolution. So what does this say? P or Q and negation Q or R. Okay. So what is this equivalent to? Okay. Between P and Q, I know at least one is true. Between negation of Q and R, I know at least one is true. So what conclusion can I draw regarding P and R? The conclusion that I can draw is at least one of them is true. Okay. Meaning this Q I can eliminate. Fine. Is it clear, this law of resolution? Between P and Q, at least one is true. Between negation of Q and R, at least one is true. So Q and negation Q, both of them I can see here. So we can simply remove that and say that between P and R, at least one is true. Is this clear?
Yes.
Right. I think one thing I forgot to mention. This P implies P or Q. This is also called as addition. Law of addition. Fine. So let me give a couple of notes and we can stop for tonight. So let me start with the proposition. P implies Q. Then Q implies P. What is this called? There's a name for this, right? If I swap the premise and the conclusion. We already seen this over here. That Pythagoras example. It is called the converse. Okay, converse of this implication. And if I take negation of P implies negation of Q, then what is this one called? You guys know this or not? The names. This one is called the inverse. And after this comes the contrapositive. For contrapositive, what should I write? Yes. Negation of Q implies negation of P. And these two, they are equivalent. Okay, meaning if this this implication, if it is true, then the contrapositive, that is always true. I was already mentioned that in this law of the contrapositive. Now let's quickly verify this. I'll take P, Q, P implies Q, negation Q, negation P, negation Q implies negation of P. Zero, 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 1, 1, 0, and 1, 1. Negation of Q will be 1, 0, 1, 0. Negation of P is double 1, double 0. P implies Q is 1, 1, 0, 1. Negation of Q implies negation of P. This is 1. False, wherever it is, I can simply put 1. true implies false, that is the issue. These two, they are the same. Okay. And one other thing I'll say, we have 5 connectives, right? The thing is, for realizing all 5, only 2 basic connectives are needed. Okay, so you can either take negation and conjunction, or you can take negation and disjunction. You can take other combinations also. These two, I consider them to the basic ones. For replication, we already know the law. This conditional disjunction only. Okay, for P implies Q, I can write it using negation and disjunction. By implication also. Okay, directly it's not, I have not given, but we can simplify. That's the whole point that I'm trying to make with this. Fine. Okay, then I think I'll stop here. In the next class, I'll continue with this. I'll take up a lot of problems. Fine.
Yes.
Okay. Okay then. Thank you guys for your time. I'll see you guys in the next class.